So, but I want to go over at least one example for the uncertainty principle. So, if you have a harmonic oscillator, simple harmonic oscillator, a mass attached to a spring. If you have a mass attached to a spring, it oscillates, right? The potential energy, so uncertainty here. You remember last time we said the uncertainty in position, let's say the x position, times the uncertainty in the momentum along the x direction also, is always greater or equal to h bar over 2, right? It's an inequality. At minimum, at best, it's equal to h bar over 2, or more. Right? That's the best case scenario, it's equal to h bar over 2. Now imagine you have a mass attached to a spring. What's the potential energy if the spring, the force constant of the spring is k? What is the potential energy if you stretch the spring by a distance x?
Kx.
The force is kx, yeah, almost kx, yeah. So it was, you integrate the force, right? 1/2 kx squared, right? 1/2 kx squared. In fact, just remember from mechanics, the force is minus the derivative of the potential energy, right? So if you take the derivative, you get minus kx, which is Hooke's law, right? Yeah. Right? Kinetic energy is 1/2 mv squared, right? And we said we can write the speed, the kinetic energy, we can rewrite it as momentum squared divided by 2m. Do you remember this? And because if you plug in mv for momentum and you square it, it will come back to this. So the total energy is this. That's the total energy. Okay. And we're going to do the simple harmonic oscillator with the quantum one. We're going to go over it in the next chapter. But we can estimate actually the energy levels, or the lowest energy level of the simple harmonic oscillator by using the uncertainty principle. So that's one of the applications that I want to do with the simple harmonic oscillator. So use the uncertainty principle to estimate the lowest energy. Use the uncertainty principle to estimate the lowest energy. So how are we going to do that? We're going to say the momentum is approximately equal to the uncertainty in momentum, and the position is approximately equal to the uncertainty in position. So meaning this, we're going to just say this. We're going to estimate that x times p is approximately h bar over 2. Again, what was h bar again? Well, how is it related to Planck's constant?
H over 2 pi.
H over 2 pi, good. Yeah. So whenever they put a bar, it's basically that quantity divided by 2 pi. Like for example, lambda bar would be lambda over 2 pi. Here's a joke. What is pi bar?
1/2.
1/2, yeah. Pi over 2 pi. Yeah, it's going to be 1/2. Okay. So here's, anyways, so P is going to be basically h bar over 2x, right? H bar over 2x. We're going to plug it here, and we want to find the x that minimizes, or the minimum potential energy, the minimum total energy. So E is going to be P squared. Here's P, we're going to square it. So what do we get? We get h bar squared, right? And then over 4, yeah, 4x squared, and then there is a 2, so it becomes 8 x squared. Can you tell me, or confirm or not this one? Can you confirm that this is correct? Anyone? Okay. And then plus 1/2 kx squared. So let's find the x that would minimize the energy. X that would minimize the energy. What do? I think the procedure is clear. You take the derivative, right? Set it equal to 0. So you get dE dx is take derivative, becomes a 4 here, you get a minus h bar squared over 4m x to the minus third power, and then plus k x equals to 0. We can multiply by x to the third power, so we get, and then move things to the other side, so we get this. K x to the fourth power is equal to h bar squared over 4m, I think. Is that correct? Yeah. Okay. And then divide both sides by k, right? Divide both sides by k, so k goes here. And so that means x squared would equal to just h bar over 2 times the square root of m times k. That's x squared. I just need x squared because x squared are the ones that show up here. Okay. So this is the x that would minimize the energy. Let's plug in to get the energy. Let's plug in here. So get h bar squared over 2m, h bar squared over 8m. So the energy, the minimum energy, is going to be h bar squared over 8m times 1 over x squared. 1 over x squared, so just flip this, so you get 2 mk over h bar, 2 mk, square root of mk over h bar, and then plus this one, 1/2 k x squared, k times x squared, here is x squared, h bar, over 2mk flips up, and this becomes a fourth, so we get, and then h bar squared over 2, h bar squared over h bar is just h bar, so we get h bar squared over 4,
Just h bar.
h bar, thank you. And then m is in the square root and I have an m here, so this just becomes k over m square root. Tell me if you agree with that. Sounds good? Yeah, good. And then plus, half times a half is a fourth, h bar, so let's put that h bar here. And then this one here, k over the square root of k just becomes the square root of k on top. And this becomes h bar over 2, k over m, minimum, You remember from simple harmonic motion, what is the square root of k over m when something is oscillating? Omega, that is omega, yes. So this is 1/2 of h bar omega. Yeah. And this turns out actually to be the true value for the ground state or the lowest energy state for a quantum simple harmonic oscillator. Okay. We're going to do more examples on this. And but with this, any questions on what I have done so far today?
Why is that the minimum?
Because we took derivative, set it equal to 0, so that's the x that would minimize it. It would minimize the energy. Yeah. You can see that the minimum will not happen at x equal to 0, right? Because x equal to 0, this diverges.
Yeah.
And it's not going to happen at x equal to infinity, because at infinity, this diverges. So somewhere in between. Yeah. Well, the next chapter is going to start with quantum mechanics. What the book does is they try to motivate the basic equation of quantum mechanics. So just like Newton's laws of motion, when you study Newton's laws of motion, I do teach mechanics every now and then. Students come out of high school or to an algebra-based physics, they come really excited to the calculus-based physics. You know what the excitement is? We're going to finally use calculus to prove Newton's laws, right? And then what do you learn? You can't prove them. Newton's laws, they are called laws. They're laws of nature. They cannot be proven. You can only do experiments to double check them or confirm them, right? So we'll not pretend to derive Newton's laws. Same thing with Schrödinger's equation. It's a basic law of quantum mechanics and it cannot be derived. You can kind of try to motivate it, but it will not pretend to be deriving it. Just here's an equation and it describes physics at the atomic scales very well, and we're just going to take it as a fundamental law of and then try to be able to use that law and apply it to problems. And we're going to start with the simplest problems, just like with Newton's laws. We start with this, at rest. Newton's first law says if it's at rest and the net force on it is 0, it will remain at rest, Newton's first law. Then you do simple, more and more complicated problems, right? A block sliding down an incline with no friction. And then you add more and more and more layers of sophistication to it. And that's what we're going to exactly do. We're going to introduce this Schrödinger equation, and then we're going to apply it to simple problems, and then get familiar on how to use it. Okay. So we're going to do that next time.